Hi, everybody. I'm Shelby Lockhart from AMD. And this morning, our first talks are on something pretty exciting, which is networks for large language models. Each of our speakers is going to get 25 minutes and then 5 minutes for questions at the end. But as Matthew said, you can obviously still post questions in the Slack channel, and hopefully he will be very amenable and answer them after. So yeah, I'll go ahead and turn it over to Weiyang, and he's going to talk about a low-cost, high-performance network for training LLMs.
Thanks for the introduction. I'm Wang Frank from MIT, and today I'm going to talk about our work on building a low-cost, high-performance network for training large language models with training subparameters. So LLMs, or large language models, are arguably the most disruptive invention in the recent years. And it is no secret that large language models training is very resource intensive. Today, the almost 4-year-old GPT-3 model already required 355 years if you want to train it on one of NVIDIA's V100 GPUs. And most recently, the Llama 3.1 405 billion model took over 16K GPUs to train in 57 days. And our conversation with Manya indicated that the next generation of large language models could as well take over 32,000 GPUs to finish training within a reasonable amount of time. And if you build a network for such a scale with the state-of-the-art approach, that will cost you $153 million and will have a network total power consumption at the peak of 4.7 megawatt. And that is very significant. But in this talk, I'll show you an alternative design that our proposal achieves near optimal performance at 23 to 62% of the cost and 25 to 63% of the power consumption while achieving the same performance as the state-of-the-art. So let me just give a brief outline of this talk. So I'm going to start by talking about state-of-the-art approach. It's a network called Real Optimized Network for large language model training. And in order to improve upon this network, we kind of begin by looking at large language model traffic patterns. What can we do with it? And then based on this traffic pattern, we raise our proposal, which is called a real-only network. And then we ask a few research questions and potentially raise a few challenges on building this kind of network. So let's begin with the state-of-the-art approach. Okay, so let's look at how people are building a network to train large language model or an entire cluster to train a big data model. So the state-of-the-art approach is called a real optimized network. And in this type of network or cluster, we have each K GPUs shown here grouped together and connected with a high bandwidth interconnect. Here, a group of this server I'll refer to as a node in the later part of this presentation is usually some sort of like a server. For instance, NVIDIA's DGX boxes can connect up to 8 GPUs with with a set of NV switches. Newer designs, however, can expand this number. And for instance, NVIDIA's GH200 supercomputer could connect 256 GPUs with 2 layers of NV switches. And we refer to again, this sort of like local node as we're just going to call it a node. Sometimes you might hear me say the word high bandwidth interconnect. That refers to the internal connection. And these connections provide extremely fast full bisection bandwidth. For instance, the current generation of NVLink can provide 450 gigabytes per second, sort of like both-way communication. And the upcoming B100 generation even doubles that number. And the large cluster consists of multiple of these nodes. And in this one, I have M of them. So for each of these nodes, we label the GPU from 1 to K as their rank. So here, and have labeled them on node 1 from 1 to K. And the term rail here in the real optimized network refers to all the GPUs with the same rank across the entire cluster or the same index across the entire cluster. So in a real optimized network, all GPUs in the same rail are first connected to the same set of switches. Here, I have shown rail 1 that connect all GPUs that has a rank 1. So the red highlighted switch here connects all of the GPUs with the ID of 1. And similarly, we connect the rest of the rails. And here, rail K is also highlighted in blue color. This connectivity ensures that GPUs on the same rail has the lowest network latency, since the communication will happen the most commonly among these GPUs. And these rail switches, in turn, are then connected to a layer or layers of spine switches to form a full bisection cloth network across all of the GPUs. So the network bandwidth in the switch or the network domain follows from what we have for data center today. For instance, it's going to be 400 gigabits per second. And that is much slower than within a node. In this talk, I'll refer to this part of the interconnect as the NIC domain or network domain. So let's look at some examples of a real-world state-of-the-art network. So the figure here shows a 1024 or 1K GPU cluster built with DGX 100 boxes, which has a node with 8 GPUs within each one. And this example uses 128 port switches. Hence, each real switch will connect to 64 GPUs downward and has 64 app links. And here, the thicker segment to the spine switch refers to like 16 power links together, and each spine switch here will have 128 downlinks. So that are the standard designs. And what are the problems? The problem is that they are getting too expensive and power hungry. And so we look at the network cost and power at this large scale, where the network cost here refers to the total cost of building a network of the switch and transceivers using 400 gig 128 port switches for a DGX GH200 based cluster. And the network power here refers to total power of switch and transceivers at full utilization. So here on the left, on the X and Y axis, I have the number of GPUs and the total cost respectively. And as the number of GPU goes up, the network cost quickly increases, and it would cost over $300 million to build a full bisection network to support all 64K GPUs. The story here is similar for power, where at this scale, at 64K GPU, 6 megawatt of power is required just for the network at high utilization. And there has to be something that like we as network researchers can do to mitigate this situation. Namely, we want to look at the workload and ask, is it even necessary to build this state-of-the-art full bisection network for a large language model training? So that's where we enter our second part of the talk, where we look at our workload, large language model training traffic patterns specifically. So let's dive deep into it. How much of this network is being utilized by the training traffic? And we look at this by looking at the training traffic pattern of different parallelisms for training GPT-like models. Here, parallelism refers to how we distribute, that is how we split or replicate the models on our cluster. The most prevalent large language model training strategy today is a hybrid between three things called data parallelism, tensor parallelism, and pipeline parallelism. In this talk, we will not dive into the details of each for now, but we know that the way how large language model is distributed guarantees that a pair of GPUs in the network will only carry at most one type of traffic. So in this plot, we show the traffic type distribution of large language model presented in the Maxon LLM paper, where the models are distributed among a cluster of DGX A100 servers. So each one of these servers has 8 GPUs. Here on the x-axis, we have the different model size, and so different models. And the y-axis shows how many pair of GPUs is carrying a certain type of traffic. So basically, if we imagine all of the GPU pairs, and there's going to be, like, we have n servers, there's going to be n squared, roughly, amount of them. And the y-axis shows how many percentage of this, like, n squared GPU pairs is carrying a certain type of traffic. The plot here shows that pipeline parallelism is the most common traffic in this example. However, even in this case, notice that the y-axis is very small. In fact, large language model training traffic is very sparse in nature, that about 99.5% of the GPU pairs actually will carry no traffic at all. This observation starts to pose questions on the real optimized network design, where we want to provide a full bisection network connectivity among all of the GPUs. Is that even necessary? So we further look into more details of the training traffic and to see where exactly the traffic is happening in this network. So where like this less than 1% of traffic is going on in our entire network. How we see this is through these traffic heat maps. So here on the left, I have plotted the traffic heat map of training a 1 trillion parameter GPT model calculated from its given parallelization strategy in the Maxon paper on 3000 or 3072 A100 GPUs to be exact. So the plot here on the left shows the first 192 GPUs, or this is the first 4 pipeline stages of this training. Remember, we had this thing called pipeline parallelism. And here, X and Y axis represent the destination and source GPUs respectively. The 2 diagonal lines here actually shows the pipeline traffic. And if we zoom into one of these pipeline stages, we can see the other two type of traffic from tensor and tensor and data parallelism. And so just to be very clear, we're assuming like a ring-based collective strategy here for those of you who are like very technical on the collective side. So the traffic here are already very sparse. Now what I'll do is I'll overlay this with two other colors as this. Here, all of the orange squares indicate that two GPUs are in the same node, so they can enjoy the very high bandwidth interconnect within this node. And hence, in this case, that's every 8 consecutive GPUs. And where the red or pink squares here on the diagonal line are the GPUs that are in the same rail. So because that's all the rank 1 for every like node, that's going to be GPUs that are every 8 ID apart from each other. We note an important property. First, we see that the network traffic is sparse, and the network traffic outside of the node is very light compared to internal to it. And more importantly, we see here like all of the traffic that actually exits the node are overlaid with these red squares. The network traffic here never actually exits the rail. That is an important observation. And in fact, we want to claim that for training GPT models with an optimal 3D parallelism, that is pipeline data and tensor parallelism, the network traffic actually will always stay within the rail in the NIC domain. So let me show why this is the case. There are two types of traffic that are going to happen in the network domain. It's basically either collective communication from data parallelism and tensor parallelism, or a point-to-point communication from pipeline parallelism. I'll show you why both stay within the rails. So for collective communications, the goal of these type of traffic is generally to achieve some data distribution target. And to achieve these targets, there are many different algorithms that we can use to achieve it. In particular, if the cluster uses hierarchical collective communication algorithms, then the traffic will actually never exit the rail. So I will not go into the details of every single algorithm, but we'll provide a simple example here for the altogether collective. For this collective, starting with each GPU carrying one data shard, the goal is to have each GPU to have all of the data shards. As you can see here, we want to go from the left configuration where everyone is carrying one different square to everyone have all of the different, rectangles. So in the hierarchical algorithm, how the algorithm runs is we first run an altogether within each rail, as shown here in this animation. So each of the GPU on the same rail sends its data shard to its peer to achieve this configuration. Here, each GPU only needs to send one data shard over the entire network, and it's within the rail. And the next step is of the algorithm gathers the data within each node to reach this final data configuration. So we see that the traffic here only have to traverse each of the rail and within each node. And the network traffic here, because we don't even show the spine switch, it never have to exit any of the rail here, switches here. So that was for collective communication with an example. For pipeline parallelism, it's a bit more involved if we want to explain it without diving into the exact detail of large language model parallelization itself. So I'll skip the details for pipeline parallel. But we know that as long as we place the corresponding shards and replicas from tensor and data parallelism on the same rail, then the traffic will stay within the rails. So in conclusion, the traffic stayed within the rails, which has great implication to our network design. And that's where our proposal comes out, the rail-only network. With this knowledge, we see that a significant portion of the network is idle in the state-of-the-art rail-optimized design, where we connect every single GPU together in a full bisection fashion, or even oversub fashion if you want to, in the network domain. And as a result, we propose to build a network with a rail-only design. Conceptually, what we're doing here is instead of having a full bisection connectivity across the entire set of GPUs, we only want to ensure each rail itself forms a full bisection network, and we can ignore the connectivity across the rails. So using the illustration we had about before, a rail-only network kind of look like this. Note that compared to the state-of-the-art rail-optimized design, we no longer have these spine switches. But that was the figure was here just for an illustration. So the design sounds very straightforward. We just get rid of the spines potentially. That's the easiest way to understand it. However, there's a lot of research questions to answer. To begin with, how do we actually realize one of these networks in a real cluster instead of just conceptually easily storing away the spine switches? And secondly, we don't build a network even like a large network with really high demand for large language models just for training one type of model. In the future, other models may pop up, or large language models may evolve where we can start to have cross-rail traffic. How do we deal with these traffic? Can the real-only network without interconnectivity across rails still handle those? So that's the second question. And also, so we started by like saying the state-of-the-art network is very resource intensive. So what is the cost and power implication of our network, the real-only network? And does it actually have any performance impact? So let's answer each of these questions separately. First, how do we realize this network? Again, the trick here is simple. I've mentioned it a little bit. We want to use the least amount of resource to ensure full bisection bandwidth within each rail or for each rail only. And then we do whatever we have to ignore the connectivity across rails. Let me show you what I mean by this. The design here is best illustrated with some examples. We used the network design we had previously for this 128 DGX H100 cluster where we have 128 nodes. Each node has 8 GPUs in it. So let's follow our easy concept first, right? We remove the spine switches. Now notice that all of these uplinks are becoming idle, so we don't have to have them. So we can also remove them. However, since each of the switch here have 128 ports, we have 64 idle ports on each of the switch. And that means we can connect each of these switch down into the GPUs again. But because each of the switch here has 128 ports, it can actually connect all of the 128 GPUs on the same rail on one of the switches. So as you can see here, I've added connection that after I remove the uplinks, I've converted all of them to downlinks to GPUs. And in this case, we don't need a second rail switch anymore. And so this is how we achieve a full bisection network connectivity for each rail only in this cluster with 128 port switches. So let's look at some numbers here. The original network takes 20 switches and 2688 transceivers to build, while the real-only network here, as you can see, only consume 8 switches and 1152, about a half amount of transceivers. And in this case, if you work out the number, we're going to save $1.3 million in cost and 41 kilowatts of power compared to the real optimized network, the state-of-the-art design. So at larger scale, this number will be more significant. So that was sort of a conceptual illustration or like an actual illustration of how to achieve our this network. The second question is, although we have shown that for large language models, the traffic will stay within each rails, there could be other models or cases where cross-rail traffic happens. Can our network handle that? Well, the answer is yes, as we can use the intranode very high bandwidth connect to forward the traffic. Let me show you what I mean by that. And in fact, actually, this model that has cross-rail traffic already exists these days, like the sparsely gated mixture of expert or MOE-based LLMs. Again, we will not dive into the detail of how MOE works and how it generates all these weird traffic, but we know that under certain cases, MOE can generate what is the exact opposite of a sparse communication. As you can see here again, on the left, I've plotted the traffic communication matrix calculated from the DeepSpeed MOE paper for a MOE 1.3 billion traffic with uniform token distribution. And the communication here is actually O2O. As you can see, every GPU is communicating to every other GPU in this example. And in the state-of-the-art network, the traffic can obviously just traverse through the spines. If I have this blue square here from the node 1, GPU 1, and it wants to talk to GPU 2 on node 2, I just go through the spine and reach the destination. Now we have removed the spine. How do we deal with this? Well, recall that real-only network makes sense in the first place because we have this internal to the intranode very high bandwidth interconnect. In this example here, we have NV switches. Therefore, we can use this intranode interconnect to forward the cross-rail traffic. And for example, for this traffic square we had before, if GPU 1 in node 1 wants to send traffic to GPU 2 on node 2, what we can do is have the data to first be moved to the second GPU on the node 1. Then it will be on the same rail as the GPU 2 on the other node, and then we can use the rail switches to reach the destination. So an immediate question here for this is the overhead. How much are we going to slow the traffic down by doing a forwarding? And in fact, that's part of the third question we want to answer, the cost, performance, and power implication of our real-only network. So we have seen that for a 3D parallelism LLM, the standard ones, the training performance is actually not affected at all because we're just removing the switches that are not carrying any traffic. Next, I'll show you that even for the other type of traffic, the overhead is small, yet the cost and power savings is significant, as you can see here on the slide. So let me talk about why that's the case. Let's look at performance first. In general, forwarding here imposes something called a bandwidth tax. This is a term quoted from UCSD from the early reconfigurable network works. So the bandwidth tax comes from the fact that the total traffic in the system increases when you're forwarding traffic. And the forwarded traffic can potentially compete with direct traffic. What I mean by this is, for instance, the forward traffic we just saw here in the previous example. If we also have traffic from GPU1 to GPU2 on the same node within node 1, shown as this red square, then this red traffic will be slowed down as it's potentially competing bandwidth in the NV switch domain with the blue traffic. This is potentially detrimental for regular data center network. But in our particular case, the performance overhead of forwarding is actually small due to the fact that the intra-node bandwidth is just way faster than in the internode or in the network. In fact, if you work out the numbers on DGX H100 system, if you do a store and forward to get the worst case overhead of forwarding traffic, it's going to be the ratio roughly of the network domain to the, I call it the high bandwidth domain or HP domain, which basically refers to the intra-node bandwidth. So the network here is 400 gigabits per second, and the intra-node, the HP domain bandwidth is 3.6 terabits per second. And if you work out this ratio, it's only 11.2%. And this overhead is sort of the worst case as well. This overhead will even be lower if there's no competing traffic and we can pipeline the forward. And that's not the end of the story. Furthermore, the traffic here requires forwarding is only a small part of the overall traffic in training. So let's look at the traffic distribution of these training this mixture of expert model we had before. On the right, we have the same heat map as before. And the left plot here shows each type of traffic by percentage volume, where here each bar is a communication from a different parallelism. So we don't have to, again, worry about the detail of how each parallelism works, but notice that the red bar here is the only one that represents an O2O traffic. So if you sum up all of these like dense communications, it's going to be the red bar. And if you go by volume, that's 26.5% of the total communication. And only these 26.5 of this communication is going to be slowed down by this 11.2% overhead. And even furthermore, a training iteration consists of both computation and communication. And therefore, like the overhead of forwarding only slow down part of the communication. And by Amdahl's law, the overall impact of training performance is negligible in this example. Okay. So that was the performance number. How much cost did we save in getting this like overhead, in exchange from this overhead potentially for a very dense communication pattern? How much cost did we save from getting rid of like these extra switches and transceivers in the network? So here we plot the network cost reduction for a cluster of 16K, so 32K and 64K GPUs, where here a K is 1024. So the biggest scale here is 65,536. And that's built with NVIDIA's DGX GH200 supercomputers. So each of the node here refers to 256 GPUs connected together with a high bandwidth interconnect. And we plot this for different switch radixes. Here, a switch radix refers to how many ports you have on a switch. So a radix of 64 means a 64-port switch, basically. So here is the result. The network cost reduction here ranges from 38 to 77%. And this would amount to US dollar of 170 million to 234 million in the case of a 64K GPU cluster, which is a significant saving. I'll just note here, like the pattern doesn't look very regular here, but you can notice it has a few discrete levels of reduction. This kind of stems from how many layers of your cloud or factory network you're saving by going from a full bisection network over the entire set of GPUs into building a full bisection network for each rail only.
4 minutes.
Okay. Yeah, and here we look at the power saving as well. And similar to the last slide, we plot the power saving for the same cluster for the peak network power consumption. This is what you would have to like budget when you're building a network. And the network power reduction here has a similar story where it ranges from 37 to 75%. And that amounts to 1.7 to 6.9 megawatt in the case of a 64 K GPU cluster. And so I think I'm almost time. So let me just jump into the conclusion slides. So yeah, that's it. And that's most significant part of the talk. In this work, we study the traffic pattern of large language model training, and we review the network traffic is sparse and stays within a particular group of GPU that we call that are basically a rail, that are the GPUs with the same rank across all of the uh, servers or nodes. And based on this observation, we proposed the rail-only network, a new network architecture specifically designed for large language models. And as a result, the rail-only network leads to 38 to 77% of cost saving and 37 to 75% of power saving compared to the state of the art. And thanks, everyone. Please let me know if you have any questions.
Thanks so much, Weiyang. That was really great. And with that, I think you can post questions in Slack.
Mhm.
If we have any, you can also raise your hand, I think. Do you have the Slack open, Weiyang? I do. It's okay if you don't.
Yeah, I have it.
Okay. Looks like we have some people typing. So I guess I can go ahead and ask a question while people are typing. You had looked at a couple different models, you said?
Yeah.
And so you got the same results for all of them?
Yeah, so that is true. And basically, what we also kind of did is sort of in this slide, if you look at like how large language models are parallelized today, there's a few standard ways of how you want to parallelize them, right? Like, and all of these parallelism, when you mix them together, kind of result in a traffic pattern that are somewhat, well, not like exactly similar if you go by heat map, but like qualitatively, they have the same property of like we have these three type or potentially four if we include another parallelism called context parallelism type of traffic. And all of them have these pretty distinct property that if you distribute them in the cluster in a like way such that like basically what I'm saying is there is a way that you can always distribute these parameters in the these models in the cluster such that the traffic pattern will somewhat resemble this, where you will have no traffic across network rails. Yeah.
Okay, I see. All right, we have some questions in chat now, I think.
Oh, okay.
Ram asked regarding the routing and rail networks, does it support adaptive routers?
By I guess by adaptive routing, you mean I just want to clarify, like if you like load balance the route across in the network domain or in the forwarding path. I mean, I guess my answer, like either way, would be it would like so basically, if you need more than one layers of switch for each rail, potentially you can connect a few rails together, even for the rail only network. Then you can do the same switch configuration as how you would do it mostly for a rail optimized network, where you just would have only communication going within the rail, right? Like, there's no communication really happens with across the rails. And for forwarding, the story is a little bit trickier, where you have to like sort of schedule the traffic of like within the node, and for the forwarding traffic in like a smart way, such that like you try to minimize the computation. But like in theory, yes, we can do adaptive routing across this cluster. In the real world, we probably have to take some careful like even sort of like steps when we actually implementing it.
Okay, let's see. We have another question. Oren, can you explain the latency impact for all-to-all and rail-only networks by going over the high bandwidth interconnect, PXN, for balanced all-to-all and unbalanced all-to-all?
That is a great question. So in a regular case, or like in if it's a balanced O2O, where I'm assuming you mean like a uniform communication, you're sort of adding in one hop of like forwarding. So the bandwidth cost is what I was referring this like 11.6%. That's actually because if you have a uniform like O2O, in a sense, every traffic is trying to compete with every other traffic. So that's where you kind of achieve a worst case performance of this like overhead of 11%. And the latency, like other than like adding this bandwidth cost part, it's going to be sort of like how fast you're traversing through this like NV links, NV switches, and then to the next rail. And it potentially actually has some, if your traffic is like not very communication heavy, right? Like the latency could actually, latency performance could actually improve. That's why, as you mentioned, PXN was initially implemented because you don't have to go through like this potentially very high layer of spine switches, right? The network latency here is still higher compared to a local NVLink latency within each node. So you're potentially not adding more hops in essence. And if you have an unbalanced O2O traffic, that starts to depend on how exactly the traffic looks like. If you end up having more competition on one of the link, then it's going to be slower. If you have, the other way, you potentially have like some of if your traffic is distributed in such a way that like the forwarding doesn't really compete with each other or doesn't compete with direct traffic, then it's going to achieve a potentially better performance. And if you go by like link latency, the number of hop itself, it depends again on the exact network scale, how many layer of like high bandwidth or like interconnect you have, like with switches, how many layers of network switch. I think in general, if you're talking about like going from a 3-layer factory into this kind of like 1-layer forwarding, you're more likely than not gaining a little bit in the latency performance. But it depends on the like exact scenario.
Thanks, Weiyang. I think we
Thank
should
you.
maybe take the rest of the questions offline and you have access
Mhm.
to the chat so that we can bring our next speaker out.
Mhm. Thank you.
Yeah, thank you.
Mhm.